Okay, let's conclude PPP. So in general, you will see, you have seen PPP has, it uses CRC. It still uses CRC, but because it's implemented in driver, so the CRC calculation is done in software instead of hardware, which is not what it was meant at a time that the protocol is designed. And fortunately, it's not a big deal because PPP is not used in the backbone. It's used in the access line. So the bandwidth would not be too big. And PPP has, compared to HDLC, PPP is simplified that it has no sequence number, no acknowledgement, no flow control. Okay, so if you want to make PPP more reliable, it's possible. There's an RFC, which is RFC 1665, sorry, 16.3, 1663, IFC 1663. It is an extension of PPP trying to make PPP more reliable. So if the implementation, PPP implementation support that, then it's possible to add those error control mechanism back to the PPP. But if the implementation does not support or does not implement that RFC 1663, then the error control is simplified to just one CRC, just one error detection. And still no acknowledgement, no flow control. But here I'm just saying that there's an extension, protocol extension of PPP that can add up back. Okay, the next section on section number should be 3.3, 3.3 section number on Ethernet. And Ethernet is the dominant wired protocol, link protocol. And so we look at the evolution of Ethernet, and then the MAC protocol, and then some selected topics. The evolution is evolved into 4 directions. One is from low speed to high speed, so it's getting faster. And it was originally 2 megabit per second, 10 megabit per second. Then it become 100 gigabit, 10 gigabit, and now the standard bodies are discussing the 40 gigabit. 40 gigabit per second and 100 gigabit per second standards. So the speed is getting higher and much higher. And then from shared media to dedicated media, meaning from broadcast link to point-to-point link. Okay, and we will see when the bandwidth gets larger, you could not use the Ethernet as the broadcast link anymore, because CSMACD, the protocol, would not scale. It would not scale as the bandwidth increases. So the shared media is only for the 100 megabit per second Ethernet, but up to from gigabit to 10 gigabit, it's all point to point. It's all dedicated medium. And then from LAN to MAN to WAN, meaning originally it was only used in local area network in the office, in offices. But later on, people are trying to move it to first mile or last mile. Okay, trying to replace DSL. In fact, some enterprises Well, if it's an enterprise requiring more bandwidth, then you would not be satisfied with DSL. The DSL would not be enough. The DSL is okay for home and SOHO, but not okay for enterprises. I mean, for an enterprise of over thousands of employees, then you cannot rely on DSL. Then you would alternatively, you would have something called EPON that we will see later, which is used in the last mile or first mile, and it's called MEN, metropolitan area. And then it also evolved into the WAN in the backbone. So right now, a lot of backbone are using 10 gigabit Ethernet. Okay, and of course they are point to point, no longer broadcast link. And the medium is getting richer. Originally, it was coaxial cable. Coaxial cable first, and then evolved into twisted pair. So most likely the Ethernet interface or the line you will see, the interface will be RJ45. The connector will be RJ45, and the line will be twisted pair, category 5 or category 6. So that's the majority. But as you evolve to high speed gigabit, 10 gigabit, then and if you need to travel long distance, then twisted pair is not enough. Then you would need to use optical fiber. So in the standard that travel quite long, over several kilometers, or you need to have high bandwidth, then those standard they use optical fiber. So it evolved in these 4 directions, and in this with these milestones. So from early 70s to the first commercial. I think the first commercial Ethernet is in early 80s. That's the first commercial Ethernet. And in 90s, it's getting very popular already. And then it starts to shift to gigabit. So that's where's gigabit? Okay, gigabit here. So you will see gigabit here, and then 10 gigabit, and also first mile. Okay, and then 3 years ago, they start to talk about 40 and 100 gig. And that's the dimension of bandwidth. It grows in this direction, and that's the medium of the standard use. So as you see that as you go higher bandwidth, then if it's short distance, then you can still use a twisted pair. You can use twisted pair even for 10 gigabit per second, but only at short distance. But if you need to go for long distance, then you need to rely on optical fiber. And the protocol layer, that's a link layer with logic link control and some other sublayers. So these are sublayers of the link layer, and some of them are optional. The Ethernet frame format. Remember, we have seen that the frame format of HDLC and PPP. They use what? Bit stuffing, right? But in Ethernet, they don't. They don't use bit stuffing. They use what? They have a preamble, and then start of frame delimit, which is also the 8-bit pattern with 0 and then 6 consecutive 1 and then 0. Okay, the same bit pattern that we use for PVP and HDLC. And then data destination address, source address, and type and length. Type and length. The length will here it will show us the total length of the frame. So I don't need what? I don't need a end of frame delimit. I don't need an end of frame delimit here, because I only need this, and then type and length to tell when the frame is going to end. And then the data, and then FCS, which is CRC. And it's 4 byte, so it's a 32-bit CRC. So the preamble is to signal the receiver. So the transmitter will send a preamble, which is long, quite long, 6 byte long, to signal the receiver, telling the receiver, hey, I'm coming, I have a frame coming, so pay your attention now. And once the start of frame delimiter shows, the receiver will know, okay, it comes, and then it would accurately, capture the bit pattern to tell which is which. Okay, so that's so no bit stuffing here in Ethernet. Only by preamble to signal the receiver, and then length, type and length. And on Ethernet, because if the transmitter is not transmitting, if no station is transmitting, then the channel is idle, the link is idle. So the frame is not back to back. If before the transmitter transmit the frame, the link might be idle. The link should be idle. So I need to use the preamble to get attention from the receiver. So that's the purpose. I need to use the preamble to get the attention of the receiver, to synchronize the receiver clock. Okay, and there's another frame format, which is a tech frame, that we would explain later in VLAN, virtual LAN. Okay, so there will be two extra fields compared to this format. You have a VLAN protocol ID and then tech control. Okay, that we would explain later. When you partition, when you try to partition the network into virtual LAN, then you would use this format. And again, the encapsulation and decapsulation process. So here's an example of frame transmission. As we mentioned that if you have multiple byte field, then you will need to care about the byte order. I mean the order of bytes being transmitted. And since IP is big endian, so you start from the high order byte. Okay, but within a byte, the bit order also matters. And because Ethernet is little endian, so it means that the order of bit getting transmitted within a byte will be starting from the low order bit first. Okay. So what happens is that what you do is that you transmit within each byte. Say this is 6 bytes. The source destination address is 6 bytes, so you transmit from the high order byte first, but with each byte you transmit from the low order bit. And it makes, in order to do the synchronization, we mentioned that there's a block coding, which is called 4B, 5B coding, block coding, or AB, 10B coding, block coding, right? It would transform the 4-bit pattern into 5-bit. So 4-bit is transformed into 5-bit. And we will pick some specific pattern from those 4-bit pattern set. So we would use 16 of them in order to make sure the clock, in order to get enough transition within within the signal. Okay, that's 4B, 5B block coding. We have explained that in chapter 2, the physical layer. And then with this, the line coding can be simplified into NRZ inverted or MLT3. So we would then do the line coding to transmit this 5-bit pattern. Okay, so these are then transmit into signal level. Okay, so it does combine the line coding, simple line coding scheme with the block coding. And before that, you would need to do the little endian bit order and big endian byte order transmission. Okay, so that's the way it works. And here the little endian bit pattern, bit order is this. You transmit from the low order bit first to the high order bit within a byte. Okay, next let's talk about the protocol, CSMACD, which is the core of Ethernet. To put it into simple words, it says that you need to do carrier sense. What does carrier sense mean? It means you listen before transmitting. You listen to the carrier to see if the channel is idle. If it's not idle, then you don't transmit. So you listen before you transmit. And multiple access, MA stands for multiple access. It means multiple stations are sharing the same channel. And collision detection means if more than one station transmitting over the channel, there will be collision. And if there's collision, then stop and back off. Back off means you try later. And every time you try, you listen. If you listen to find busy, then you keep listen. You keep listening. If it's idle, then you transmit. If you transmit, you collide. Then you stop and back off. Okay, that's the to put it in simple words. However, it's not simple as this. It has a more specific detail in the steps. It says that you have a frame ready to transmit. You have assembled the frame, and then you need to check whether the channel is busy, and the channel is half duplex. If it's full duplex, then what? You don't care. If it's full duplex, you don't wait. You don't keep sense. You don't do channel carrier sensing. You just wait an interframe gap to allow interframe gap and then transmit. So if it's if it's a full duplex link, meaning you can transmit directly. You don't need to do carrier sense. Nobody will compete with you. The link is used by you and also your peer. And because it's full duplex, then It means that you can transmit at the same time when your peer is transmitting, and there's no collision. So that's full duplex. So if it's full duplex, then you go ahead. Don't wait. You just have an interframe gap and then transmit. But if it's half duplex and the channel is idle, so if it's half duplex and channel is idle, then you go ahead too. You go ahead to wait interframe gap and transmit. And if it's half duplex but the channel is busy, okay, so that is true, right? So it's true, yes. Then you keep what? You keep looping. You loop here. You keep sensing whether this is or the condition get changed. Of course, it will still be half duplex, but the channel might get idle later. Okay, and the checking here is not done by software; it's done by hardware. So you have a piece of hardware that keeps sensing, and once it senses idle, it would then go this way. Okay, it's implemented in hardware, not in software. Okay, then if you transmit, if it's half duplex, and you have collision, what happened? If half duplex and you have collision, then you go here, and you send a jam frame. You send jam. Why you send jam? Before you stop to back off, you send the jam, and then increase the variable, which is a variable attempts. This is a counter to keep how many times you have tried, how many attempts you have tried. And if it's too many attempts, say the standard say 16. If it's over 16, then you give up. You give up. You don't try anymore. The transmission is failed, and you give up. You interrupt the CPU and tell the CPU and put it in the status register, telling the driver that it's failed too many times. So you give up. Perhaps the too many collision usually means two possibilities. One is the traffic load is too high, which is unlikely. And another possibility would be there's something wrong in the hardware. Perhaps something wrong in the network. Perhaps there's a buggy interface card. Keep sending signal, so I have no chance to transmit. Or every time I transmit, I got collided. Okay. If it's not too many times, if it's not 16 times yet, then I back off. And how much time do I need to back off? There's a binary exponential back off. Binary exponential back off here to determine how much time I would back off. The binary exponential back off says that if it's the first time collision, then you back off 1 unit. You pick a random value, but within 1 unit of back off time. If it's the second time you fail, you collide, then you back off 2. You pick a random time within 2 units of time. If it's the third time, then it's 4. The fourth time, then it's 8. So be 1, 2, 4, 8, 16. And so your backup time is getting longer and longer every time you collide. Okay. Until 16, then it will be 2 to the order of 15. 2 to the order of 15, the backup time. So the backup time will be getting longer and longer when this counter is getting higher and higher. So you wait a backup time, a random backup time, but random from a certain value, an exponential value, and then go back here to check whether it's the channel is idle again. Okay. And now, why do I need to send a jam frame? Why? Okay, if I have collision, I just abort. Should I just abort and then back off? It says that in order, if you have collide, maybe the collision is only one big collision. What happens is if another station is finishing the transmission, when you are starting the transmission, and it's finishing the last bit, that station is finishing the last bit of its transmission, and you have started your first bit, and your first bit overlap with its last bit, so you have collide only one bit, and it's possible that the collision is only one bit. It might not be heard by the others. Perhaps we heard it here, but the one bit collision might not be heard by guys over there. So even though we are in the same link, in the same collision domain, perhaps some station might not hear the collision. So in order to make sure that the collision is heard by the station here and also the station there, to be heard by all the stations within the link, we need to make sure the collision is loud enough. It's loud enough. And the way to make sure the collision is loud enough is to prolong the collision by sending a jamming signal. Okay, so I prolong the collision. If I have collision, I send a jamming frame, which is a special pattern, to make sure the collision is long enough. And so we both, if I collide with your frame, you send a jamming frame, I send a jamming frame, and the signal level will be high and long enough, to be heard by all the stations on the network, on the link. Okay, so that's the reason why you send a jam, to make sure the collision is loud and long enough to be heard by everyone on the link, sharing the link. Okay, so you go this way. But if no collision, then I finish the transmission, no collision, then it's done. If it's not done, okay, I loop here. So see, this is I start the transmission, I check here, and I continue to transmit. Once the transmission is done, it's successful. Is there an egg? When I finish the transmission, is there an egg? Do I expect an egg from the receiver? No, I don't. On Ethernet, you don't expect an egg from the receiver. You finish, it's successful. If you don't finish, then it's not successful, it's failure. But if you once you finish, it's successful because I'm sure that the frame is received by the receiver, and whether the frame is correct, it has been checked by the receiver. But I don't care. The chance for a frame in error is very low, so I would assume that the frame, once transmitted and received, it's correct. The chance for error will be low. And if indeed there's an error in the frame, then it's up to the upper layer protocol to detect the error. I don't handle that kind of error at the link layer because the chance for error rate is very low. And it's major that the link error at Ethernet is lower, much lower than something like 10 to the order of -9. 10 to the order of -9. So they don't expect acknowledgement here. Once transmitted successfully, the chance is that it's correct. So no need to get an egg. Okay, that's this part. And at the receiving part, you will see that it's simple, that you would just check whether the reception is finished. If the reception is finished, then I do a sequence of check. I check whether the frame is too small. It's not. It's up to the standard. And then when the address is me, recognize the address. The destination address me is destined to me, so I should receive the frame. If it's not for me. I don't need to receive the. I will just drop it. And actually, it would. Okay, I would just drop it and then look back. Okay. And if it's for me, then I check whether the frame is too long. So here I check whether it's too small. Here I check whether it's too long. If it's too long, then it's an error. An error, I will come here. So coming here, I will generate interrupt. I'm going to tell the driver, I receive a frame for me. This frame is for me, but the frame is too long. So there's a problem. So the driver needs to handle this kind of error. Also, it will check the frame check sequence, CRC, which is calculated by hardware to do the check. And then octet boundary, correct. And then successful reception. So this is the Ethernet. And one question is why you need to wait an interframe gap? Because it doesn't like the frame transmitted back to back. It needs to have a frame, a gap between two frames. Okay. Okay, just an interframe gap. This happened the same. This happened too in wireless LAN. They also have some interframe gap. Okay, if you calculate the maximum frame rate, so given that when we say it's a 100 megabit per second system Ethernet or 1 gigabit per second Ethernet, how many frames can we transmit at most? So let's do the calculation. A minimum frame would occupy this. Okay, you need 7 bytes preamble, as we have seen. And you need 1 byte for start of frame delimit. And then you have 64 byte minimum frame size. And then you need a 12 byte interframe gap. Okay, that's the total. 84. That's 84 byte. And if it's a 10 megabit per second Ethernet, how many frames can you transmit at most per second? Then it'll be 10 multiplied by 10 to the order 6 divided by the number of bytes, minimum frame size in bytes multiplied by 8 bit per byte. So you got 14,000 frames, about 14,000 frames. So if you got 100 megabit per second Ethernet, then that Ethernet alone can pump 148,000 frames, 148,000 frames per second. And with 1 gigabit, then it's over 1 million frames per second. So keep the number, remember the number. On gigabit Ethernet, one link alone can generate over 1 million frames per second. So that's very demanding for a switch or a router to handle. If you are a switch or a router, you need to handle this amount of frames, 1 million, over 1 million. And to make it worse, because the switch or router would have not just one port, it would have multiple ports. So it's a switch might have 24 ports or 48 ports. If it's 48 ports and each of them is 1 giga, then and each port is generate 1 million frames per second, then you would have 48 million frames per second. That's a lot. That's a lot of frames to process for a switch. Okay. And as we move on to high speed, higher bandwidth, we encounter the problem of the half duplex versus full duplex problem. The half duplex says that only one station can transmit over the channel. So you run CSMACD. That's the original Ethernet design. That's the original protocol. But when it becomes full duplex, on gigabit Ethernet released in 1997, it says that simultaneous transmission is possible, and it's a point-to-point channel anymore, and it's a point-to-point channel, not a broadcast channel anymore. So then you virtually have no carrier sense, because every time you do carrier sense, it's idle. It's idle. And no multiple access, only you are accessing the point-to-point channel in that direction, and no collision detection, because no collision at all. So then that's a pure point-to-point channel. And the necessary and sufficient condition for full duplex will be you would have simultaneous transmission and reception without interference, without interfering each other. So transmission and reception at the same time on this point-to-point link, and dedicated point-to-point link with exactly two stations, two peers, and both stations are capable to configure in full duplex mode. Full duplex mode. Okay, so an interface card could be configured to half duplex or full duplex mode, and most interface card can do auto configuration, meaning they can auto detect to see whether they need to operate in full duplex or half duplex mode. Okay. So that's and if it's half duplex, the way to do flow control in Ethernet is by back pressure. And I mentioned that back pressure means that it could be done either in forced carrier or forced collision. Forced collision. Forced carrier means that you send for the receiver to slow down the transmitter. The receiver say, "Hey, you transmit too fast, and I can't accommodate." Then it will send a forced carrier, so that the transmitter will sense the channel busy. Once the transmitter senses the channel busy, it will stop. It would keep listening without transmission. Forced collision means that if the transmitter sends something, and then this frame is come too early, I need to process other frames. So I cannot handle the new frame. So I collide the frame. Directly. If I collide the frame, what happened to the transmitter is it will back off. If I send forced carrier, the transmitter will defer, will keep listening, keep sensing, keep carrier sensing without transmission. But forced collision will even put the transmitter into back off. So you would wait a period of time and then come back to listen. Okay, that's for half duplex. But if it's full duplex, then you don't need carrier sense. You don't have collision. So you need something else to slow the transmitter down. And that's by sending an explicit pulse frame. You send an explicit pulse frame to the transmitter to slow it down. And as we move on to gigabits, you will find something, the half duplex would not work anymore. So within say within 100 megabit per second, we can have auto configuration. Okay, by the interface card 100 megabit per second Ethernet could work in dual mode, half duplex or full duplex, and it could do auto configuration, auto sensing to sense whether it should work in half duplex or full duplex. But on gigabit Ethernet, we can do that, but there's a problem. The problem is this. Consider station A and B, and station A the first thing that happened is that station A sent a frame to someone, perhaps not B, some other station, but the signal propagates to B. The frame propagates to B, and if the first bit is about to reach if the first bit from A, if the first bit from A is about to reach B, and B does carrier sense, B will find that the channel is idle, right? Because the first bit hasn't reached B. So when B does carrier sense, it will find the channel idle, and then B transmit immediately. So if right before this reach B, B does carrier sense, and it's idle, so I'm free to transmit. I transmit a frame, and then immediately it collide. They collide with each other, and the collision signal will propagate to A, right? And so how much time does it take, in the worst case, for the collision signal to reach A? That'll be round trip time. So in the worst case, that's the first bit would take a one-way propagation time, and then got hit here from the frame by B, so it would take another one-way propagation to reach A. So the worst case is the round trip time. Within one round trip time, A detect there's a collision. Okay. If A is still transmitting the frame, that's fine. It would do what? If A is still transmitting the frame, then it would continue to send the jam frame, the jamming signal. It will send a jamming signal to make sure everyone knows there's a collision. Okay. What happened if before this round trip time, A has finished its transmission? If A finished here, this frame is so short, it's finished here, and the collision signal was heard later after I finished the transmission. Then there's no chance to send a jamming signal. See, in this flow chart, if I'm sending the frame here, okay, I'm sending frame here, no collision, sorry, it's here, no collision, and I finish the transmission. So it's done here, so successful. So since I finished the transmission, and I think it's ended, it has succeeded. So I have no further action for this frame. It's done. It's a done deal. I have no chance to go back here to send a jam, right? For A, it's a done deal, and I'm out of the loop. I was in the loop here. In the loop, I have sensed the collision. I can come here to send a jam frame. But now, since I'm out of the loop, the transmission is done, I have no way to send a jamming signal. I'm done. So this is what happened if A finished the frame before it hears the collision. Before the collision signal comes back, then it will be a big problem. The CSMACD failed totally in this case. And would that happen in Gigabit Ethernet? Yes, it would. Because of what? Compared to the cable length or the propagation time, the frame time is short. Why the frame time is short? Or frame size or frame time is short. Why? Because I'm transmitting a gigabit. I'm transmitting faster. So I would take less time to transmit, right? So if I finish the transmission fast, then the frame appearing in the cable will be short frame. So the chance will be, compared to the cable length, the frame is short. And I can finish the transmission early. So the chance that it would be finished before the round trip time will be high. The chance will be high. So for the CSMACD to work correctly, there's a principle. It says that the round trip time 2t, that's the propagation time, the round trip propagation time should be smaller than the transmission time for a minimum frame. Transmission time, this is propagation time, this is transmission time. The round trip propagation time should be smaller. If the transmission time is too short, then it will be reversed. See, the transmission time is too short, then it will be not large enough than the round trip propagation time. Then it will become this. Then it's a problem. It's a problem. And the chance that this time will be short, the transmission time is short in gigabit is much higher than 100 megabit per second Ethernet, right? So the chance of violating this will be high. So CSMACD will fail in this case for Gigabit Ethernet. And it did happen. It indeed happened. And the solution is this. It says that, okay, if you send a frame that is short, then make it longer. Make it longer. How? Still have, even if you finish the frame, still continue to send the carrier signal, sending something dummy signal, as long as you continue transmitting. Don't go out of the loop. Don't go out of the loop here. If you go out of the loop, everything is over. If it's not out of the loop, you might still come here. But if you are out of the loop here, then it's done. So it says that keep the channel busy by sending extension carrier. Okay. Another way is frame bursting. Because the frame is too short, then you would wait for several more frames before you transmit. Okay, you aggregate several frames together and then transmit them all together. But these two are both stupid, right? Because you are sending something dummy, and this is stupid too because you are waiting for several other frames to come before you can transmit the first frame. Okay. So for the delay, it's bad. For the channel utilization, it's bad. Although there are solutions for Gigabit Ethernet half duplex mode, but half duplex is still a failure. So in the market, the Gigabit Ethernet is only running a full duplex mode. So you would not, in the market, in the product, you would not see half duplex Gigabit Ethernet. It'll be just a full duplex. Okay, that's because of this problem. I finished transmission fast before I sensed the collision detection, which is a bad thing. Okay, as we go even higher to 10 gigabit Ethernet, Of course, it's full duplex only. And it's not for the local area market, it's for the wide area market for long distance. Another new product is the Ethernet in the first mile and or the last mile. And you will see some new physical layer like EPON, Ethernet PON, passive optical network. So these are the new standard, but they haven't prevailed yet. They still need to grab the market share piece by piece. Okay, the final one is the CSMACD implementation. It's in hardware, and it's from the opencourse.org. Yeah, opencourse. The opencourse website, and it's in Verilog. And I would leave this to next week. We'll talk about the module, the architecture. But first of all, let me give you a concept of how they do IC design. When you need to design an IC or an IP, intellectual property, a circuit design, what you would do is you need to draw the block diagram first. And this is the block diagram with the modules. With modules, say here you have seen 5 modules with an Ethernet core. With an Ethernet core, you see 5 modules. One is host interface, and then MII management module, and receive Ethernet MAC, transmit Ethernet MAC, and MAC control module. So you see 5 modules here, and then you will see the signals between these modules. Okay, so you have the block diagram first. That's the first thing, and then. And then for each block, each module, you need to identify the input signal and the output signal. So you will see the input. So this is the input and output between between the host interface and the host. So the upper one will be the host machine, and this is the interface card, and this is the host interface. So you need to identify the signal here, the input and output. Some will be from the host, some will be to the host. So input output need to be identified, and it's shown here. So between host interface and the host, there'll be. Here the direction means input and output. So you know if this is input, then it's from the host. Output is to the host. And also need to identify the interface between to the physical layer, to the physical interface. So you have this with the Ethernet 5 physical layer, you have interface. And again, you have input and output. You have input and output. Okay, so you identify the input and output with other modules. And then you also identify the registers. Okay, what register do I have in control? What register can I read and write? So this, when writing a program, it's like these registers are like local variables. They are local variables. So you have input and output parameters. So in the function code, you have parameters. And some of the parameters are input, some of the parameters are output. Some of the parameters are input and output at the same time. Okay, so you have I/O, and then you would declare some local variable, which are registers, that your working space. Okay, And then that's the data structure. So you figure out the data structure first. So you draw the block diagram, and for each block, each module, you identify the data structure to be used. That's the input and output, and also the local variable, which are the registers. And then what? You figure out the logic, the algorithm. So you have the data structure. Next, you identify the logic. And logic of a module is identified by a state diagram. A state diagram. See, this is a CSMACD state diagram, transmission diagram. And this is the receive diagram. Receive diagram here. And it says that transmit. You start from here. You start from here, and well, if you have a frame and you sense, you sense, and then busy, you defer here. And if it's idle, then you come here and then start to send. So you send, the first thing you send is preamble, 7 byte preamble. And then 1 byte start of frame, delimit. And then you send data and enable. And here the nibble is defined as 4 bit. Every 4 bit is called nibble. So you transmit nibble here, and then continue. And then during the transmission, you might receive the jamming, the collision. If you detect collision, then you come here. So each of these states might come to the jam state. If you have jam, you finish the jam. You send a jamming signal, and then you come to backoff. And then backoff, you wait for random time, and then come there, go there. And if you finish sending the data, then you go to pad. Pad means that if the data being sent is too small, then I need to make it as large as at least 64 byte, because the minimum Ethernet frame size is 64 byte. So you need to add some pad, some dummy data. And then you come to frame check sequence, CRC, and then it's done. Okay, so any of this, you suffer collision, you go to the jam. Okay, so that's the state diagram. So if you got this state diagram drawn precisely, then your logic is binded. Your logic is confirmed. Then you start to write what? The parallel program. The parallel program. That you write the output signal here. The left side, that's the assignment, right? The assignment. So you write the output signal from the input signal. So the output signal is a function of input signal and the output signal and the registers. So on the right hand side you will see it's a function of these three: input, output, and registers. And the function is actually logical operations, and or not combined, or exclusive or combined together. That will do the logical operation here, and then assign to the output signal. And this is parallel program because each of the outputs could be changed. The value of each of the outputs value could be changed when a clock ticks arrive. Well, every time when a clock tick arrive, all the right-hand side will be triggered. The logical operation will be triggered and then assigned to the output signal. So the assignment is done every clock tick. Every clock tick, I change the value. So it's parallel. It's not sequential. It's at the same time in parallel. So that's the idea of writing the hardware design. I think I need to stop here. I'm 10 minutes over. So next week we'll continue from here. And also next week, please remember to turn in the homework assignment for chapter 2. Okay, see you next week.